Today, we're jumping into something that sounds like pure sci-fi, but it's actually all around us. We're talking about chaos, cause, and, of course, the legendary butterfly effect.
So, let's get right to it. The big question, the one that everyone knows. Can a tiny little butterfly, just by flapping its wings, really cause a hurricane thousands of miles away?
You know the crazy part? The answer is, well, it's yes and no. Seriously, it all comes down to how you look at the world. It's like we're about to explore two totally different versions of reality.
And to really get a handle on this, we got to go back in time a bit. Let's start with the world as Isaac Newton saw it, a perfect, orderly, clockwork universe. So picture this, a universe that works like a giant, flawless machine. That's the world of classical physics. Everything is predictable. Everything is orderly. If you could just know where every single piece was right now, you could, in theory, calculate the entire future. It gave people this incredible feeling like, wow, we figured it all out. And man, people were excited. The poet Alexander Pope really captured the mood when he wrote, "Nature and nature's laws lay hid in night. God said, let Newton be, and all was light." It felt like a switch had been flipped, and suddenly humanity could understand everything. But not everyone was on board. You had guys like the poet John Keats, who felt like all this science was, taking the magic out of the world. He worried that philosophy would clip an angel's wings, unweave a rainbow, basically turning all of life's beauty into a boring set of rules. And that tension, that's key.
And right there, in that clash between a perfect machine and a magical rainbow, is where our story takes a turn. Welcome to the science of chaos. Because, it turns out, even inside that perfectly predictable clockwork universe, something totally unpredictable was lurking.
So, what even is chaos theory? Well, imagine a system that looks completely random, just total madness. But underneath, it's actually following strict rules. The secret sauce? It's this idea of sensitive dependence on initial conditions. It just means a teeny tiny, almost invisible change at the beginning can explode into huge, wild differences down the road. This is actually a perfect way to picture it. Just think about your kitchen faucet. Turn it on low, and the water is smooth, predictable. You can turn it up a bit, and it's still pretty steady. But then, you turn it just a tiny bit more, and bam! It goes from this nice, orderly stream to a chaotic, splashing mess. That sudden switch is the key. It's a phase transition from order to chaos. And the story of how we stumbled upon this is just great. It's not some epic tale of discovery in a lab. Nope. It all started with a weatherman, a super old-school computer, and a cup of coffee. So this meteorologist, Edward Lorenz, is running a simulation of the weather. To save a little time, he decides to restart a run from the middle. But instead of typing in the full number, 0.506127, he just rounded it to 0.506. I mean, what's the difference, right? It's practically nothing. So he starts the computer, goes to grab a coffee, and when he gets back, whoa, the weather forecast was completely different. It was a whole new world, all from that tiny rounding error. And that was it. That was the aha moment. Lorenz had just accidentally discovered the core principle of the butterfly effect, that sensitive dependence on initial conditions. He proved that a tiny, almost meaningless change in the beginning can create a completely different outcome in the end. Okay, so now that we have that under our belts, we can finally get back to our butterfly. And this is where things get really interesting, because we're going to look at two totally different ways of thinking about cause and effect, the physics way and the human way. It all boils down to this. What do we mean by the word cause? If you're a physicist, pretty much everything that ever happened before an event is a cause. But for us, as humans, a cause is something we can grab onto, like a handle, to make something happen. Physicists see everything as connected. We see most of the world as just noise we can ignore for what we're trying to do.
All right, back to the butterfly. From a pure physics point of view, did it cause the hurricane? The answer is yes, it did. But here's the catch. So did every other butterfly. And a whale jumping out of the ocean, and a kid playing soccer in Scotland, and the pull of the moon. See? The word cause gets so huge, it pretty much becomes meaningless.
Okay, but what about the human answer? Is the butterfly the cause? No, of course not, because we care about causes we can actually do something about. Think about it. If there's a car crash, we blame the drunk driver, not the fact that the other person was just driving to the store. If you want to avoid a cold, you get more sleep. You don't worry about butterflies. You can't stop a hurricane by catching a butterfly. It's not a useful handle.
So what are we supposed to do with all this? Let's tie it all together and talk about why this actually matters in our everyday lives, what it says about our own actions.
Look, this whole thing isn't just some neat little physics problem. It's really about what it means to be human. In one sense, we're just tiny parts in this giant physical machine, bound by its laws. But we're also more than that, right? We have intentions. We have purpose. We try to make a difference. We act with meaning.
And that really brings us to this incredible quote from Dostoevsky. He said, "All is like an ocean. All flows and connects. Touch it in one place and it echoes at the other end of the world." And maybe that's the real point of the butterfly effect. It's not about weather prediction. It's about us. It's about realizing that every little thing we do, every kind word, every small choice, sends ripples out into the world. We can't predict where they'll go or what they'll become. We can't control the hurricanes, but we are absolutely responsible for the ripples we start.